Okay, so on this video, I wanted to show you guys about torque. We might have covered this slightly if you're in AP1. If you're in AP Calculus Physics, I'm not sure we've covered this yet, so I wanted to go over it again anyway. Wouldn't hurt to get it again. I also want to talk about cross products, because your whole lives you've been lied to slightly. So there's two ways to actually multiply things. One is a dot product. That's what you've actually been doing most of your life. When we were talking about work, when we talked about work being force times the distance times cosine theta, right? If you're having an object move in this direction, that's actually its position vector, or its motion vector, its displacement vector. We call it D for displacement, right? If that's its displacement vector, but you're actually pulling with a force like this on this object, the work that we did on that, well, the work that was up this way, sorry, the force that was done this way, actually didn't move it at all, so it did no work. The only thing that actually made this object move was the force exerted in that direction. So that's what a dot product does for you, okay? Force times distance times cosine theta was our work. Well, now we're going to do something else. We're going to do a cross product, and for the general terms of that, it's going to be sine theta instead of cosine theta. So it's going to be the other vector we're talking about. So let's talk about cross products. So torque, got a new term for that one. We got a tau, a Greek T, okay? Torque is the position vector, okay, so how far away something is from some point that you're observing from or moving from, times, and this is, notice the X there, that makes a difference, okay? R cross the force, okay? So now we've got two vectors. So this is, torque is the rotational version of force. All the stuff that we have to consider our R, our position vector with it, okay? So if we have gravity pulling down, force of gravity is working like this, okay? And we've got a mass here. If it is on the end of a rod, how much force effectively are you feeling, or how much torque are you getting out of the thing? Well, it depends on how long your rod that you're holding it by is, okay? So if I have here a mass on the end of a stick, well, most of the mass is here. Let's imagine the stick has absolutely no mass, okay? So all of our mass is here at the end. Gravity wants to drag it straight down, right? But I'm not letting that happen. So how much torque is this thing exerting if it's here versus here? Well, if I hold it here, and try this at home, get something that has like kind of an uneven end, right? Get a stick that has like a ball or a lump of clay or some Play-Doh on it or something like that. Try and hold it at the end. You'll find out that it's a lot harder. Even if you just get a regular stick, which actually has mass, right? It's going to be harder to hold it at the end than it is in the middle, right? You get more torque this way, and the reason for it is because your position vector from where you hold it, the center where it wants to rotate, to the point where the mass is actually located, that position vector, as it grows, it multiplies your force. So that's what this formula is really telling you, okay? Torque overall is basically just a force at some distance away. Something wants to turn, it wants to move, it wants to rotate, right? So your torque is going to be a rotational force. And the longer away, the farther away that is, the harder it is to hold on to it, but the more force you get if you're trying to lift something, right? So if you have a longer handle, it's a much easier task to lift this mass than if you have a really short handle. It gets a lot harder to do. It gets closer, in fact, the shorter your handle, the closer it gets to just actually lifting the object up. The longer your handle, you have to use less force to actually move it. However, there's a cheat on this, right? You get less force that it actually takes to move it, but your distance that you actually have to move it increases. You get a longer arc length you have to move it over. So you can't cheat energy. Okay, you can cheat other things, forces, you can use torques, you can use lever arms, but you still can't cheat the energy. So our torque here, how much torque do we have? Well, it depends on, again, how far away we are from the center of rotation, or where it wants to rotate, and how much mass we have on the end, okay? So for this, our torque is going to be force of gravity with R, okay? To figure this out, there's two ways of doing it. The simple and cheap way is to just really figure out the magnitude of our torque, okay? So we'll cheat a little bit. And it turns out that if you do that, you get r times f times sine of theta. Okay? And that's how you can find the magnitude of your torque. If you want to find the direction of your torque using that, well, you can't. Sorry, you're out of luck. You can use the right-hand rule, though, to set you back on track. So if you just want the magnitude, you can do that, and then you can use the right-hand rule. So how does a right-hand rule work? You have to take your right hand, okay? And you take your first vector, right? Whatever vector comes first. So in our equation, r comes first. So we have to point our hand in the direction of r, okay? And then cross f. So then you curl your fingers in the direction of your other force that you're multiplying it by, okay? And your thumb, the direction your thumb points, that is the direction of your torque. Right-hand rule, okay? So if you're actually turning a screw with the screwdriver, most of them are right-hand threaded. So that means you use the right-hand rule. This is actually, I always screwed up. Every time I was trying to screw a screw into a wall or wherever else in my entire life, I would always get confused. People would just say righty-tighty, lefty-loosey. But for me, there's a problem because a circle is a circle. Which way is left and which way is right, right? So for me, I remember it now by using the right-hand rule. If I take and I turn the screwdriver this way, my screw will go into the wall. If I take and I turn my screwdriver this way, it'll take the screw out of the wall. Still works there. And like that, weirdly enough, if these are our two vectors, r and f, okay, think about what this means. R is my first vector. I do a cross product with my force vector. My thumb is now pointing into the board, okay? So you actually, with a cross product, get a vector that is perpendicular to either of your other two vectors. We had an x, we had a y, now we get a z. Okay? So we're going to get a new notation when I draw something on the board. Imagine you're shooting an arrow out of a bow, right? If you're looking at it end on, like this, okay, so our arrow would be flying into the board with our right-hand rule. So my torque here would actually be, what you'd see is the feather end of the arrow. So that x means you're going into the board, okay? If it were going the other way, right? If we had a position vector like this and a force vector like this, r cross f would get us an arrow flying out of the board, and so you'd be like you were looking at the end of it. So it would look something like that. So that means out of the board, that means into the board. Just a little bit of, whatever convention you're going to see in the future. So for our torque, we've got a cheater way of doing it, okay? R times F times sine theta, magnitude. Right-hand rule gets you the direction. Quick way of doing it, okay? Here's the actual way to do it, okay? You've got to have, this has a direction as well as a magnitude. So if if R is equal to, let's say, positive 3. This is 3 meters over, okay? And force of gravity, that also has a direction. It's going to be minus for us. It's going to be down, okay? And it's going to be, let's say, I don't know, we'll pick a number, 10 newtons, okay? So here's the thing. We now have to consider, for doing an actual cross product, we have to consider the x, the y, and the z components of all of these vectors, okay? So we're going to use vector notation, all right? For this, r is entirely in the x direction, isn't it? There's no y, and there's no z to that r vector, that position vector. So for x, we get a plus 3, okay? For y, we have 0. So here's our x, here's our y, and here's our z. For z, we have also a 0, okay? That is our r vector. Same thing. We have to do that again for our force of gravity here, okay? In vector notation, we have to get an x, a y, and a z position here, okay? Now look at this. F has no x direction at all. It has no z direction at all. So x and z are 0 for the force vector. The only thing you have now is the y direction. And for us, that's negative 10. Okay, so now what do? Keep a hold of this. Rewind it if you need to come back to it. I'm going to erase it so I have room. Okay, now here's the part you've been waiting for, the part that everybody loves. We have to do a little linear algebra here, okay? So R was our first vector, and we're going to do it cross F, okay? So R was 3 for X, positive, 0 for Y, 0 for Z. For force, right, force of gravity here was going to be 0 for X, minus 10 for Y, and for Z, it will be 0 also. So now we're going to take and actually do the cross product, and here's how you do it, okay? You do top, this is equal to our X. In fact, I'm going to break this out into pieces, okay? Let's find our X piece first, okay? So X is going to be equal to, so here's how you find your X. You actually cover up all the numbers that have anything to do with X, weirdly enough, right? Then you do multiplication, top by bottom, okay? So here I get 0 times 0. I get 0, okay? Then I do minus bottom times top, okay? So for this, I'll get negative 10 times 0, which will be 0, okay? There's our X. Our Y part, same deal, but we cover up everything that has to do with the Y, okay? So here we do top times bottom, okay? And weirdly enough, on a Y, I'm going to show you something in a second, okay? But we do top times bottom, so we get 3 times 0, which is 0, okay? Minus, we're going to do minus bottom times top. Okay, so bottom 0 times 0 is also equal to 0. All right, so X we got 0, Y we got 0. And this is strange, isn't it? Because we only had vectors in the X and in the Y before, and now both the X and the Y are equal to 0. But let's just go ahead and keep on going and see what we find for Z. Okay, so same deal. What you had for Z, cover it up. And now do top times bottom. Okay, nothing in the Z here. We're not looking at that, right? We're looking at the X times the Y here. So you get 3 times negative 10. All right, and minus, okay, so then you get minus bottom times top, 0 times 0. And all of a sudden, look at this. Now you get a number, negative 30. So, negative going into the board, positive coming out. When you put them all together, we're not done yet. Okay, we got to take and put this into vector notation here. Okay, our X is 0, simple enough. Y, you have to flip the sign. I don't know why. This is just, there's a long explanation. I do know why. I'm not going to go into it here. It's linear algebra. When you start working with these matrices, you kind of get into it. Anyway, you have to flip the sign on the Y. Okay? So it's going to be, if it was positive before, it becomes minus now, yada yada, right? Okay, so it's 0. So, you know, if it was positive, we'd put a negative here, okay, and 0, and again, it's 0, so it doesn't really have a plus or minus, okay? And then for Z, you keep it as is, and so we get negative 30. And there's our vector, X, Y, Z. For our torque in the end is going to be 0, 0, negative 30. So don't forget, this one has to have a minus sign, okay? Everything else is exactly as you'd expect it, but for some reason, throwing it out there, Y has to have a negative sign. And torques, when you start talking about things, torques become very interesting because it's the force you get off the edge of a wheel or a lever or really kind of anything that has a mass hanging out on the edge, okay? So if I take and exert a force down like this, it suddenly becomes a torque because it's going to move about this pivot point. So I'm no longer really exerting a force out here as much as a torque. And so then you get some really crazy stuff happening, okay? Because as I go with this, notice this also. This handle isn't exactly what you'd expect. I've got another pivot point I'm going to make it do, right? It's going to want to pivot about this point right here, okay? So as I go, give it a little bit of speed here, and I'm going to explain this some more. Okay, but basically we're going to get an angular velocity. Okay, we're going to get a linear velocity in this direction. We're going to get a position vector that we're going to cross that with. Okay, so now we're also going to get, as well as an angular momentum, which we're going to talk about. Okay, we're getting an angular momentum somewhere, some way over here. And we've also got a position vector about which it's going to rotate this way. And the force here is gravity is going to give us a torque. Okay? And when we let it go, what happens is really strange because you get a cross product vector that lets you see the cross product is always 90 degrees to what you would expect it to be. And if I go the other direction with the wheel, watch what happens now. 90 degrees the other way because I reversed my my angular momentum on this. And so you get precession, is what this is called, in the other direction. And it doesn't fall down, which is also interesting. And also if I torque my wheel, if I actually exert a torque, a force upwards at a distance, about a pivot point, it keeps that torque until eventually gravity robs it away. Kind of interesting.